The person who invented the railway viaduct is a genius.
During a magnitude 8 earthquake in
Passengers thought they were doomed. However, the result was unexpected.
The bridge's overall structure was intact.
The bridge adopts innovative special bearing designs, which cleverly separates the railway bridge deck from the lower
design
structure.
allows
The bridge deck to float on the bearings. When the lower structure moves with the ground, this movement will not be transmitted to the upper deck, ensuring the stability and safety of the bridge floating deck. Here is not literally a loose connection, but through the key structure of expansion allowing the deck to move relative to the substructure. The expansion plug divides the bridge into 3 parts. Each part can move independently to some extent. The wall design is particularly unique. It is not fixed to any structure on the ground, but relies on these special bearings and expansion achieving plugs. Both flexibility and stability. The expansion plug of the box-shaped rubber structure. In addition to the flexible design, it also needs to perform well in seismic resistance. It is located in an area with the design can withstand earthquakes above the Victor magnitude 8 and withstand winds up to 260 kilometers per hour. To understand its seismic resistance, we deeply discussed the construction details of the bridge foundation. Is located on a slope with a great change in irregular slope. Engineers cut the mountain grouting using wool blocks and shotcrete to ensure the stability of the foundation, especially the rock block by drilling holes in the slope and inserting special rods, then grouted and which cured, makes the concrete block press inward, which greatly improves the stability of the slope. The steel piers and arch structures of the process is also amazing. First, the engineers built the world's tallest cable crane tower with a height of 9.15 meters used to lift the required components for the bridge. The arch structure is mainly connected by nuts and bolts. Over 600,000 nuts and bolts were used. The construction of the arch was carried out gradually until the 2 arches perfectly meet on a critical day. This process is called arch closure. To ensure the smooth progress of arch closure, engineers used special hydraulic jacks to make precise adjustments and temporary connections between the structures to deal with possible alignment issues and wind effects. When discussing the principles of bridge design, we have to mention the superiority of the parabolic arch. By comparing parabolic arches and circular heavy loads, we can clearly see that the strength and stability of the parabolic arch. The reason why the parabolic arch is the best because it can evenly distribute internal stress, forming a pure pressure providing excellent support. This is why modern bridges like the Tuna Bridge adopt parabolic arch designs. In addition, the balanced track technology to support high-speed trains. The balanced track has fewer tracks and can absorb vibrations, but also has problems of shorter service life. Despite this, its design is still designed to meet the demand that trains at a speed of 100 kilometers per hour. Redundancy was also considered in the design. Even if one pier is damaged, the bridge can still remain stable. The train can still cross the bridge at a maximum speed of 30 ensures kilometers. Safety and reliability of the bridge in extreme cases. This is a great feat in the history of human engineering. Thanks to the engineers behind this project and meticulous execution.